Hey class, this is Mr. Roberts at Shasta High School. We're looking at a homework set that starts at question 19. And it says, determine which transformation was used on each pair of polygons. Note, some may have undergone more than one transformation, but try to name a single transformation if possible. So this is kind of just a vocabulary test, right? If I look at this very first shape, it looks to me, um, when I look at these two, what are they, quadrilaterals, like trapezoids, that it's probably a single reflection that happened. And if I was to reflect across that line, right, I would get the one to land on the other. So I would say that this is a reflection. The next one to me looks like it's just a translation, right? I can see this point is translated by this vector. And this vector is the same vector that's used everywhere to push this triangle along. I mean, this is another trapezoid. Push this trapezoid along. So I think this is just translation by this vector. There doesn't appear to be any rotation or reflections that happen. So this is a translation. Translation. I believe the next one, I could say that there's a rotation followed by a translation, but if I was to put a point maybe somewhere about here, I bet that there is a rotation about that point where if I take and I rotate this way, I can get this whole thing to swing over to this spot. So I think that's why the book was encouraging us to think about a single transformation. So I could say this is a rotation about point, I'll call that point A. So there's some point A there where I could do that. And also, if you would have placed 2 there, you could set a rotation followed by a translation. That's fine. D, D, it's probably the same thing. I think I could probably think about a spot down here somewhere where I could take this point, right, and I could just rotate along and get to where it would land to here. So clearly I'm not rotating around one of the points that are on that rectangle, but somewhere off in the vicinity of where I've sketched a point, there is a point, I'll call this point B, where I could do a single rotation. Because they asked us to try and use a single transformation to describe it. So I would say it's a rotation. But I could also think about taking this rectangle, rotating it about its center, and then once it's lined up, I could say then slide it or do a translation over. So I could say rotation with a translation also for that. For E, I think definitely it's a reflection along this line. So if I just reflect across that line, so this is a reflection. Whoops, reflection. And then it looks like our last transformation here. I'm gonna say there's 2, right? What is super difficult about that is when I look at it, I initially thought, hey, can't I just slide this right angle, like rotate it so it'll match up here? It's like, wait, that's not a right angle, right? There is not a right angle there. So I think that I have to do 2 things, and I think the things I have to do is perhaps a reflection first. So I could reflect this, and I don't know why I'm going this way with it, but I could reflect this. And then after I reflect it across that line, pretty sure the reflection has to happen, I could then take this shape and I can rotate it this direction around the right angle. And if I was to rotate that around the right angle, right, it would get so that it was oriented like this with the right angle here after doing that rotation. And now I can see that this right triangle is roughly lined up with the original one that I had. So then I would just say a translation. So I could probably shorten it, but to me, I'm just right now saying it's a reflection, and I did it across this line L, followed by a rotation. And I just basically rotated it until it lined up. All the pieces were parallel to the original shape, and then there's a translation back to it. Translation. All right, so that's it for the first question. I think we're moving on to question 20. 20 says, Julia wants to play a game called Guess My Line. Oh, I like that game, Guess My Line. She gives you the following hints. Okay, 2 points on my line are 1, 1, and 2, 4. What is the slope of her line? Okay. It says a graph may help. I don't think I need that, but you might want to sketch and look at a graph. But I've got 2 points. I've got an x and a y from one point and an x and a y from another. I need to figure out how much y has changed. I need to divide that by how much x has changed. I can see that my y is starting at 1 and it's going up to 4 from if let me say this correctly, if I'm starting here and moving to this point, right? Y starts at 1 and goes to 4. I can show that arithmetically as just taking where I ended up, 4 minus 1, and I get that my change in y was 3. And then for x, I can see x starts at 1 and goes to 2. I can show that arithmetically by going 2 minus 1 is 1. So it looks like my slope is 3, right? I'm up 3 over 1, up 3 over 1. Next, it says, what is the y-intercept of her line? Well, we've got this 3 is our slope. We know one of our parameters. We know our slope parameter. What about this y-intercept parameter, b, right? So to figure that out, we are going to consider y equals mx plus b, a generic line in slope-intercept form. We're going to consider one of the 2 points we have up here. You can see we've got 2 of them. I'm going to use the second one, the one that's 2, 4. I have an x that's at 2 and a y that's at 4. And I'm going to plug those xy values into this equation. So y is 4, so this is going to become 4, and that's going to equal m, which is the number 3, times x, which is 2, and then plus b. So I have what? I've got 4 equals 6 plus b. If I take away 6 from both sides, 4 minus 6 is b. Therefore, b is negative 2. b is negative 2. So I think this is my other parameter. This is my y-intercept parameter. So the equation of the line should be y is equal to 3x minus 2. And I box this, and then the next thing I do is I come up and I think, hey, let me grab my points and try them. So when I take 1 from this equation, from the first point, 1, and I put it in there, 3 minus 2 gives me 1. That's perfect, right? It's supposed to give me 1, and I got 1. When I take the 2 from the second point and plug it into the equation, 3 minus 2 is 6, and 6 minus 2 is 4. That's exactly what it's supposed to give me. So I have, with great confidence, the equation of the line that Jamil wanted me to find. Guess my line. I got it. Your line is y equals 3x minus 2. Moving on. For each diagram below, solve for x, explain what angle properties or relationships you know. Okay, so on this first one, right, these are complementary angles. Complementary angles. And complementary angles have a sum of 90 degrees, right? They have a sum of 90 degrees. So I know that if I take the 6x, that's a representation for one of the angles, and I add to that 4x plus 10, I get, they're complementary, so they have to add up to 90. Therefore, 6x plus 4x is 10x's plus 10 is 90. 10x is 80. Therefore, x is 8. So x is 8 is the first answer, right? That's for part A. And if I want, it's probably wise for me, because I always make goofy mistakes. Come in here, 6 times 8 is 48. And then 4 times 8 is 32. 32 plus 2 more would be 30. No, wait a minute. 4 times 8 is 32. 32 plus 10 is 42. That's right, 42. And if I add those two up, 48 and 42, 8 and 2 is 10, carry the 1. Yeah, guess what? 48 and 42 are complementary. So I got the right value of x. X is 8. And this was the property I used. Complementary angles have a sum of 90 degrees. The second one I'm going to use, these are supplementary angles, or you could say they are also angles that form a linear pair. The two of them together, this angle plus this angle, is forming a line. So I would say one of the two things. I'm going to do this. I'm going to say not complementary. I just did that. Supplementary. Supplementary angles have a sum of 180 degrees. So I can combine 5x plus 13 and 3x plus 7, and I should get 180 degrees. 5 and 8 is 8, so I've got 8x plus 13 and 7 is 20, is 180 degrees. Subtract 20 from both sides, so 8x is 160 degrees. And if I divide both sides of them by the magical number 8, I get exactly x is 20 of the degrees. So, well, I don't, x is 20. X is 20. And if I plug 5 times 20 degrees plus 13 degrees, so if I plug that in, let's see, 5 times 20 plus 13 gives me 113, and 3 times 20 plus 7 is 67 degrees. And if I look at 112 plus 67, I got, I'm off by a degree. What the heck? 5 times 20 plus 13. That's my problem. I didn't think I added 13. Of course not. 5 times 20 is 100 plus 13. This is 113, and then that's 67. If I add 113 and 67, that is the 180. Yeah. Whew. So these are indeed supplementary angles. They add up to 180 degrees. So my answer to part B was that x had to be 20. All right, moving on. Determine the domain and range of each of the following graphs. Well, that's fun. Well, it looks to me, right, this thing is just going to keep going this way, right? And it doesn't look like it's going super fast this way, but eventually any x value this direction is going to pick up some kind of a value for that function. I don't think there's a vertical asymptote there. I think it's just going to keep going. So I'm going to say that my domain is I'm going to say it's all reals. Right? So if you were to write it like this, x is bounded by nothing, right? X could be anything. It's all reals. Now, different story for the y values. This clearly looks like it's an asymptote, that it's gotten so flat that I don't believe that this curve is ever going to cross across 1, right? So to me, it looks like my range is going to be, I can go like any I've never written this I haven't written this in a while. I can go any value going in the negative direction, so I'll put negative infinity, but then my y values are going to be bound by 1, and I don't want to say that it's going to equal 1, but it's bound by 1. It certainly is not. It doesn't look like the y values are going to get bigger than 1. So big idea. The domain are the x values. The range are the y values there. Let's move on to B. Very nice parent function. I recognize this. I think it's the square root of x maybe. And then it shifted to the left 3 units and shifted down 2 units. But I digress. That's a parent function we're not talking about. So for this, I would say it looks like you can put -3 in, right? And -3 is going to give you this value of -2. So I'm going to say that my range, right, these are the x values. My ranges are all things starting at -3, right, and including -3. And then it goes on forever, right? I don't think it ever stops this way, so I'll put just towards positive infinity. So it's just any, actually that's just sloppy. Let's just say x's are anything, x is anything bigger than -3. In fact, I can write it like this: x's are greater than or equal to -3. Because I don't need to talk about the other end. It just goes on forever. The domain, I just got those two words backwards. Domain. No, I did. I just flipped them. This is the, oh my gosh. And the reason why it worked is I see so many of you in the hallway showing me domain, and you're doing those horizontal lines. That's what triggered it. The domain is any x value greater than 3. That's the domain, Roberts. We keep telling you that when we walk down the hallway. Yeah, you're right. And the range looks like it's limited by below, right? It looks like the range is all y values that are greater than or equal to -2. This does look like it's growing kind of slow, but it doesn't look like an asymptote at this point. So I'm gonna think that it just continues to grow, and eventually it'll take a long time, but eventually you can hit pretty much any y value given enough time if you're going to wait for it. Let's go down here. Oh, this is a beautiful parent function. Looks like maybe a very simple parabola that is it's shifted and it's flipped, shifted to the right, flipped upside down. It's cool. It's cool. We won't talk about the function yet, but let's just talk about its domain and range. So let's get this right. Domain, right? The x values, and I don't see any restriction in the domain at all, right? I can have x values way over here, and eventually this curve is just going to keep growing and it'll hit any of those points. So I'm going to say the domain is all reals. The range, on the other hand, is clearly bounded by 0, right? You don't get anything above 0. So I'm going to say the range is y values are less than or equal to 0. It looks like y's can be 0, but y's are also those things that are below 0. So y is less than or equal to 0. All right, and then finally D. D, the way these arrows are going, right? Clearly the range, no, I just did it again. That's 2-in-1 video. The domain, thank you for doing this when I see you, for reminding me of this. The domain is all reals. And the range starts right here at -1. So y's are greater than or equal to -1. I don't have any y values. I don't have any output values. Nothing in the range that's less than -1. So that's it for the range. All right, moving on to question 33. Again, that's 2 nights in a row that we've had to do these questions where we're dealing with these fractions with no calculator, right? Listen, the truth is, at some point, we're going to have to deal with stuff like this where they're all variables. It could be just all numerical things where we're simplifying. So it's good that we're doing this, but it seems a little tedious right now. So let's just okay, we could do this. So I've got, the first one is a -7, and then there is another -7, and I've got a -5/6 and a -1/4. So that's the thing about these mixed numbers, right? When I write down -5 and -7 and 5/6, that literally is a -7 plus a -5/6, and this -7 and 1/4 is literally a -7 and a -1/4. So it helps me a lot to break these up like this so I can see them as the fractions and the whole numbers. The two -7s form a -14. And then let's see here. If I wanted a common denominator, this 4 is a 2, 2, right? And the 6 is 2, 3. So I see what's going on here. The first fraction is the 6 is gonna need another factor of 2, right? So because I know that I'm going to have to bring in this one has to have two factors of 2, and this one's going to have another factor of 3. So my common denominator is the number 12, and I can bring in those factors by just multiplying this first fraction by 2 over 2, and I can multiply the second fraction by 3 over 3. So when I do that, just beautifully, I love how this happens. This becomes negative 10 over 12 minus 3 over 12. So the beauty is now I got the common denominators, right? They're both 12s. So I can combine those together. So I've got a negative 14, don't forget about that. And then I've got a minus 13 twelfths. But there's a negative 1 lurking there, right? So I'm going to bring that out, and I'm going to rewrite this as negative 14 minus 12 twelfths minus 1 twelfth. So you see what I've done there, right? I just broke that 13 up into 12 and 1, right? Negative 13 is a negative 12 and a negative 1. This number is equal to 1, so now negative 1. So I've now got negative 15 and a negative 1/12, so I can write it as, that's awful. Let me rewrite that better. Negative 15 and 1, not 1/2, and 1/12. So that is my answer for that part. Okay, let's move on to part B. Part B has, again, a subtraction problem. We've got a negative 8, and we've got a negative 3. We've got a negative 1/2, and a negative 1/4. And that's what that is, right? I've got this right here is literally negative 8 minus 1/2. This is distributing this. It's a negative 3 and a negative 1/4, right? So that's what these are. Negative 8, 9, 10, 11. This is negative 11. And then I've got, this is not bad. This is almost recognizable, right? If I multiply this by 2 over 2, this becomes a minus, I don't know why I'm using that color. This becomes a minus 2/4, and then minus 1/4. So what we've got here is negative 11. And then 1, 2, 3 minus, and then a minus 3/4. So negative 11 and 3/4. That's the easiest one so far. Okay, now we've got a multiplication problem. Again, I'm always going to go to improper fractions when I do that. So 2 times 7 is 14, 15, 16, 17. This is negative 17 over 7. And I need to subtract from that 7. Oh no, I need to multiply that by, oh, I'm multiplying by 7. That's so exciting. By negative 7. And the reason why that's exciting is because I was dividing by 7 and the negative 17 sevenths. So the 7 over 7 is gone. It's a giant 1. I'm left with just negative 17 times negative 1, or 17. This is the number 17. That's super nice. That looks better. All right, and then the final one, D, we've got negative 2 and 1/8, and we have to divide it by 1/5. So let's see. Negative 2 and 1/8. Negative 2 times 8 is negative 16, and one more. Negative 16 and one more is negative 17. Negative 17 over 8. And instead of dividing by 1/5, I'm going to multiply by 5 over 1. Yeah, that's what I'm going to do. 17 times 5 is the beautiful number 85. And that's over 8. And 85 over 8, I think we're going to leave that alone. Oh, what? Get out. How did that happen? 85 divided by 8. Oh, yeah, it didn't happen. Is 10.625, if I looked at it as a fraction. Mr. Roberts, it sounds like you're using your calculator. I am. I get this up to this point, and this is kind of my preferred answer, but I'm just wondering if that is reducible, and I should know that it's not, because 85 times 8 No, 85 divided by, what is 85 divided by 5? It's 9, right? No, it's 17. That's a prime number. So this is 17 times 5, another prime number. And then my denominator is all factors of 2. So there's no giant 1 there. That's the answer, right? It's negative 85 eighths. So fun with fractions, 2 nights in a row. Interesting. Oh, look at this. This is my favorite. It says rewrite each expression below in equivalent simpler form so they do not contain negative exponents. And also we get rid of all any possible giant ones. So, you know, I'm awfully tempted to say, hey, -3 minus -1 is like -2, and then put it down and we're done with it. And that works, but I think I'm going to just go ahead and I'm going to destroy some negative exponents. I'm going to multiply this by z to the third over z to the third. That's what I'm going to do. And when I do that, in my numerator, I'm left with 4 times the number 1. And you may be saying, 1? Mr. Roberts, I don't see 1. No, it turns out if you multiply z to the negative third times z to the third, that's z to the 0 power. And anything raised up to the 0 power is just 1. So that's why I picked z to the third, because I wanted to get rid of that negative exponent up there. Now in the denominator, you'll notice that I also got rid of the negative exponent at the same time. And the reason why I did that is, well, there's clearly the 20 there, but now z to the negative first and z to the third is z to the second power. There's one last thing here. There's a giant 1, right? 20 is the number 4 times 5, and I've got up here a 4, and I've got a z squared. So I end up getting, this is a giant 1, and I end up getting 1 over 5 times z to the second power. 1 over 5z to the second. Moving on to b. b, I don't have any powers raised to powers, but I do have some numerical things here, right? 2 to the third power is 8. So I'm multiplying the number 8. 3 to the second power is 9, so there's a 9. And then I'm multiplying y to the 8th times y to the negative 10th. That's going to be y to the negative second power. Because I'm just multiplying them, right? It's not being raised to another power. 8 plus -10 is -2. Now I can't leave the answer this way because I've got this negative exponent, so I'm going to multiply by y squared over y squared. In my numerator I get what? Well, when I multiply y to the negative second times y to the second, that is y to the 0 power, which of course is our favorite number 1. So all I'm left with up in my numerator is 72 times 1, or 72, and my denominator is y squared. So I've got 72 over y squared. And then, let's see, last one, I'm raising something to the negative third power. I could go one of two ways. I could raise each of those things inside the parentheses to the negative third, right? Or, and that's raising to the power. I'm not multiplying both of them by -3. I'm raising it to the negative third power. Or I can simply say, look, let's get rid of the negative third power. I'm going to take 6g to the third. I'm going to raise that to the third. And then my denominator, I'm going to do 6g to the third. I'm going to raise that to the third. The beauty of that is in my numerator now I've got 6g to the negative third and 6g to the third. I'm sorry, 6g cubed to the negative third and 6g cubed to the third, which gives me 6g cubed to the 0 power, which is just the number 1. So my numerator is 1. My denominator is, I can write this now as 6 to the third and y to the 3 times y to the 9th. 6 to the 36 times 3, let's see, it's 3 to the, it's 20. No. 6 to the third is 216. So I get, for my final answer, 1 over 216 y to the 9th power. Yay. By the way, if you want to get an exponent in your TI calculators, right, that symbol right here, that kicks it up into an exponent. So if you were to, it would look like this on your screen. 6 to the third on one of the older ones. But on the newer ones, when you hit that symbol, it'll go 6 and it'll put it up there in the exponent for you. All right, let's move on to what? We're done. That's it. Okay. Well, that's the end of that assignment. We ended up at question 24, and you know where to find me. I'll see you around here later. This is Mr. Roberts. Talk to you later.